Hi, and welcome to our review of the key attributes of functions. This is going to cover how to analyze any given function, thinking about the key features we need to discuss when we really think about the characteristics. So the first thing we need to do is think about function notation, because I think we struggle a little bit with what the notation even means. So you'll see things in a math test like f of x equals 3x plus 1. What does this mean? Well, our input is our x value. So our input is x, and our output is f of x. So what we're saying is, in this function, if we plug in an x value, that's our input, take that x value, multiply it by 3, and add 1 to get the output. It's a pattern. 3 times our input plus 1 equals our output. And this would generate an infinite number of ordered pairs, an input and an output put together. So for this function, if we had an input, let me get my tools here. Let's make this a little smaller. If I had an input, x equals 2, my output would be 3 times 2 plus 1, which is 7. So we could say our input is 2 and our output is 7 for this function. We could also write it as an ordered pair. We could say 2 comma 7. Or we could say f of 2 equals 7. These are all important ways to express inputs and outputs. So let's go over here. If we're looking at this example, we have an ordered pair x comma y. And this first value is always going to be written as x. So you're always going to see it being written as x. But we could write our y as f of x. We have to remember that that's another way of saying y. So if I translated f of 4 equals 8 into the other forms, I could say, let me make this a little smaller so we have room for both forms. We could say x equals 4 and y equals 8. Or we could write it as an ordered pair. We could say that this is 4 comma 8. Okay. Let's look at this second example. You're being told that f of x equals 10 where x equals 3. So we could think about it as an ordered pair. Ooh, again, let me make this smaller. I could say it's 3 comma 10. Or I could decide, okay, they're telling me that x equals 3 and y equals 10. Our input is 3, our output is 10. All right, let's take a look at a basic function that you're used to seeing. Oh, before we do that, I'm sorry, we do that, we need to cover intercepts. Intercepts are a really important key feature of a function, and I think we struggle with what they mean algebraically. So if we think about our graph, our x-intercepts are where y equals 0. So we could say that they all follow the format x comma 0. So if we have an equation to find the x-intercepts, we plug 0 in for y and solve for x. Graphically speaking, we can say that x-intercepts are where the function crosses the x-axis. Y-intercepts are the reverse. There is our y-intercept is where our x value is 0. So we could write it as an ordered pair 0 comma y. On a graph, our y-intercept is where the function crosses the y-axis. So let's take a look at this example, this first function. This is a common function that we're used to seeing, x squared minus 9. You studied this at the end of Algebra 1. And I think we would decide that this is a parabola because it's an x squared graph. So if you had the graph itself, it would be easy to identify some of these key attributes. We could say that our y-intercept is down here. Oops, what happened to our circle? Our y-intercept is down here. And we have two x-intercepts, right over here and right over here. So our y-intercept, if we count it, is at -9. And our x-intercepts, if we count it, are at -3 and +3. We could tell from the graph that the domain is all real numbers because our graph goes out to the left forever and out to the right forever, and it continues everywhere in between without any breaks or holes. Our range is not all real numbers, though. We have to be careful. If we look and scan our graph from bottom to top, we would say that our lowest y value is right here, and we decided that was -9. So our range would be from -9 all the way up, so to positive infinity. So we could say y is greater than or equal to -9, or we could use interval notation, and we'll get into that in a sec. But say we didn't have a graph. There's a distinct possibility we would be asked to analyze this function without a graphing calculator. So here's a couple of the questions we could be asked. We could be asked for something simply like f of 2. And what they're saying there is, when x is 2, what is our y value? If x equals 2, y equals, I don't know. Well, all they're asking you to do here is plug in 2 into your original function. So we would say that f of 2 equals 2 squared minus 9. And we could just do the math there. 2 squared is 4 minus 9 is -5. So we would say that f of 2 equals -5. We could write that as an ordered pair, or we could write that as a statement. We could say that there's the point 2 comma -5 on our graph, or we could say f of 2, equals -5. And if we go back to our graph, that's a reasonable answer. At an x value of 2, our y value is -5. So that's one of the key features you could be asked to find in a function, which is the output for a given input. Okay, now let's think about x-intercepts. X-intercepts without a graph involve solving an equation. So here we need to solve the equation where we plug 0 in for y and solve for x. Our x-intercepts, let me make this smaller. Our x-intercepts are, where y equals 0. Let's make that smaller, that's too big. So we need to solve the equation. Let me write this down. Let me get a slightly smaller pen. We need to solve the equation. There we go. 0 equals x squared minus 9. We're plugging in 0 for y and solving for x. So if we had to solve this equation, we'd have to add 9 to both sides to get x by itself. So we get 9 equals x squared. And then we'd have to square root both sides. And when we do that, we have to be careful. In the middle of solving an equation, when we square root both sides, we need to remember to put a plus or minus sign in front. A plus minus sign, because we have two answers. We're going to have the positive square root and the negative square root. Okay, so let's go back to our original equation. What we're saying here is that the square root of 9, both positive and negative, is equal to x. So we'd say that our answer is positive 3 and negative 3. Those are our two intercepts. And we confirm that with our graph, positive 3 and negative 3. Those are the two values that you could plug in for x that would make our y value equal to 0. So if we're going to write that as an ordered pair, we'd say 3 comma 0 and negative 3 comma 0. Or we could write it using function notation. F of 3 equals 0 and f of negative 3 equals 0. Those are many different ways to express where the function has x-intercepts. Okay, for y-intercepts, we're going to do the opposite. We're going to plug in 0 for x, because our y-intercept occurs where x equals 0. So let's go back to our equation and plug in 0 for x. So what we get is f of x, that's our y value, equals 0 squared minus 9. Well, that's not so bad. We can solve f of x equals 0 squared minus 9. Well, that's negative 9. So our y-intercept is negative 9, and we can confirm that with the graph. There's our y-intercept at negative 9. So we can write it as an ordered pair. We can say 0 comma negative 9, or we could write it using function notation. We could say f of 0 equals negative 9. Okay, we decided from our graph that the lowest point is negative 9, and it goes up forever. and it goes out to the left and right forever. So there are many ways to express domain. We can use interval notation, which would be negative, I'll write it, infinity to positive infinity. I'll draw an infinity symbol in 1 second. Negative infinity, there we go, to positive infinity. That's interval notation. And we use parentheses because we don't include the values in negative infinity, positive infinity. Those are just concepts. A different way to express that is to say all real numbers. That is a good answer as well. All real numbers. Because we can plug in any value for x. X can take on any value. Our range was not all real numbers, though. Our lowest y value was -9. So we use a bracket, we say -9, and then our graph goes up forever. So we'd say all the way out to infinity. So let me draw the infinity symbol. Our range is from -9 on up. So from -9 to infinity. Or we could use an inequality. Here we could say y is greater than or equal to, and I'll put the equal to sign in a second, -9. Because we're only allowed to have y values bigger, let me move that, sorry, than -9, and -9 inclusive. There we go. No matter what number we plug in for x squared, we're never going to get a y value less than -9. Because let's think about it. If we plug in a really big number into x, we're going to get a really big number. But if we plug in like -1,000,000 and square it, we're going to get a positive number. So when we square things, we're always going to get a positive number. So the absolute smallest we could make x squared is 0, right? No matter what we plug in for x, it's always going to end up being positive after we square it. So the smallest y value we're ever going to get is -9. That's our range. So our minimum and our maximum. Our graph is a minimum point right down here. That minimum point is the ordered pair. Whoops, let me write it. Our minimum is the minimum at 0, -9. We don't have a maximum because our graph goes up forever. All right, let's try a slightly harder function. This is a funky one. The square root of 16 minus x squared, and that whole quantity plus 1. So when we're evaluating this, we need to ask ourselves certain questions. What happens when we plug 0 in for x? What is f of 0? Is there any spot on the graph where our y value is 0? That's the question, where is f of x equal to 0? And then we should also consider, are there values of x that we're not allowed to plug into our function? And we should also ask ourselves, are there y values we will never be able to get as an output? So no matter what value we plug in for x, will we never get certain y values? So if we look at this slide, I'm showing you the graph, but we could do this problem without a graph. So when we graph this, we get an arc. That's part of a circle. And if we're just looking at the graph, we're going to notice that our graph has firm endpoints. It has a firm endpoint right here and right here. Those are firm endpoints. I wish they would want me to fill this circle in. Those are firm endpoints. Our graph starts and stops at those points. That's the ordered pair -4, 1 and +4, 1. So just looking at a graph, we can tell that our domain runs from -4 all the way up to +4. That's where our domain is right here. Our range is from our lowest y value. If we scan our graph from bottom to top, our lowest y value is 1 all the way up to our highest y value, which is 5. So there's our range from 1 to 5. When we're considering how to do this without a graph, we need to do the algebra. So if we look over here, we need to think about where our x-intercepts are. And we said that x-intercepts are where f of x equals 0. So if we plug in 0 for f of x right here and solve, we start to solve, so we add 1 to both sides, subtract 1 from both sides, and we get -1 equals the square root of 16 minus x squared. And what you're going to notice is, if you take a step back and ask yourself, am I ever going to be able to get an answer of -1 if I take the square root of something? No, you're not. There's no solution to this equation right here because there is no x value that we can plug in that will make the square root of some number be -1. So this graph does not have x-intercepts. there are no x-intercepts. And if we look at the graph, we can confirm that. Our graph is completely above the x-axis. There are no x-intercepts here. Our y-intercept is always where we plug in 0 for x and solve for y. So if you look over here, I plugged in 0 for x. So we get the square root of 16 minus 0 squared plus 1, which is the square root of 16 plus 1, which is 5. So we'd say that our y-intercept is the ordered pair 0, 5, which we can confirm on our graph. When we plug in 0 for x, we get a y value of 5. That's our y-intercept. If we were thinking about these endpoints algebraically, we need to ask ourselves, are there any x values that we're not allowed to plug in? Well, we can remind ourselves that you can't have a negative number under a square root. So there are definitely going to be some x values we can't plug in. We need to ask ourselves, what x value would I have to plug in to make the number under the square root negative? And let's think about it. What number squared would be bigger than 16? Well, x values bigger than 4 or less than negative 4 end up creating a negative number under our square root. So we're not allowed to have x values over here to the left of negative 4 or to the right of positive 4 because they will produce a negative number under our square root. So we'd say that our endpoints are at an x value of negative 4 and positive 4. And when we plug those in, we can get our y value. So f of negative 4, when we plug in negative 4, we get the square root of 0 plus 1, which is 1. So here's one of our endpoints. Right there. That's negative 4, 1, which is right here on our graph. That's an endpoint. And then our other endpoint is when we plug 4 into our function. We get 16 minus 4 squared plus 1. The square root of 0 is 0 plus 1 is 1. So here's our other endpoint. That's 4, 1. So if we figured out our endpoints, we would say that our domain runs from negative 4 to 4, and our range runs from 1 to 5. This is an interval notation. I also want us to be able to see it written as an inequality. So we could say for our domain that, hold on, let me get this down. We can say that negative 4 is less than or equal to x, which is less than or equal to positive 4. Put the equal to signs underneath. That's our way of writing our domain with an inequality. We can say for our range that 1 is less than or equal to y, which is less than or equal to 5. We can have y values between 1 and 5 inclusive. So this is how we think about the key features of a function, either given a graph or algebraically if we don't have a graph. Thank you.